Okay, let's get started. Um, Start off by talking about the homework. First thing, load up the RStanArm and the BRMS package. You can tell it to use multiple cores. If you read the message that comes up when you do, library RStan or library RStanArm, it will tell you, it mostly suggests that you use all the available cores, but there's an exception to that, which is if your computer doesn't have enough memory to do like 4 processes with this data set in simultaneously, then that can actually make things go slower if your computer has to swap from RAM to disk to hold the whole thing in memory. So I think, the GSS, I cut it down to try to avoid that problem, but I think some of the problems some people may have had were just, trying to do it on a computer that didn't have enough RAM to run the things in parallel, and then it kind of almost completely grinds your computer to a halt. So first question, it was about, thinking about a model. You could choose it and write down some representation of the posterior distribution for that. I chose a question on, it was first asked in 1988, and then it was asked again in the 2000s about gay marriage. And so there were 5 valid answers, from strongly agree to strongly disagree, asking people what they thought about that. So for the variables I used to predict that, I chose age, which is, I think, one of the most recognized variables is to predicting people's opinions on social issues. Also the gender of the respondent. And I also included a dummy variable in this case to answer the question, what religion were you raised at the age of 16? Not necessarily what religion do you hold currently, but what you had when you were 16 years old. So in that case, the model could be expressed like this, and I gave you the first couple lines of something like this for you to use, even though you had different outcomes and maybe different predictors. So we have this observation mechanism mapping your sort of, utility or how latent variable y star for how much you support the outcome, and that is divided into these observed outcome categories that we see on a survey: strongly agree, agree, neither agree nor disagree, disagree, strongly disagree, etc., depending on where they fall relative to a set of cut points. There should be, even though I wrote tau 5 there, the actual last one should be tau 4. So there would be 1 fewer cut points than there are number of categories in order to divide the sample space of that y star into the observed outcomes that we see. So you can try to put a prior on the cut points. Oftentimes you don't really need to. In RStanArm, we do something that's a little bit more complicated, which we haven't talked about yet. In BRM, in the BRMS package, I think by default it's going to do improper prior on those taus, but subject to the restriction that they're in increasing order. So the type, if you look at the underlying scan code for these cut points, it's always an ordered type, which is a specialization of the vector. So that's really the only prior information we're putting on those, is the logical constraints that cut points have to be in increasing order. And that's basically to say, if you agree that, anyone should be allowed to marry anyone, that puts you sort of farther to the right in y star space than if you say disagree with that sentiment. So then we need how is y star generated. In this case, I have an intercept coefficient on age, gender, and then a coefficient for the dummy variables on each of the religions that were available to choose among for something like that. The error term of that for an ordered logit model is assumed to be standard logistics, so mean 0, scale 1. And then you say, okay, I've got all these betas and lambdas. The betas, even though you can't do this exactly in the same way in stan_polar, but you can imagine for the later questions, thinking that the beta, the coefficient on these variables at time t, you can think of this as a common coefficient for that variable, or vector of coefficients for those variables beta, plus some time-specific deviation in that coefficient. So it may be that the coefficient on age changes over time in addition to people getting older over time. I meant to put the lambda up there as well, but the lambda variables I didn't think varied by time, although possibly it could. You know, if the sort of religious leaders of your religion, you know, come out with an updated statement on their policy on gay marriage or something like that. The important part of this was to then say, okay, these B's, they have a multivariate normal prior with a mean of 0 and some Cholesky factor that's the product of a diagonal matrix of standard deviations and a Cholesky factor of a correlation matrix. So you can put any priors you want. We talked about something more complicated, which is what Stan GLMER does, but something that's in the same lines but simpler that BRMS does is you just put standard deviations on the diagonal elements of delta, or those are standard deviations, you put priors on those. So if you want a one family prior or one parameter prior that is restricted to be positive, the exponential is a good choice. Its mean is 1 over the rate parameter. So if you put in 1, here you're saying, okay, exponential prior on these standard deviations with a mean of 1. And then the typical thing to do in Stan for a prior on a correlation matrix is to use the LKJ distribution. And if you set its shape parameter equal to 1, then that's saying all correlation matrices among how the elements of B differ from one time to the next, all the correlation matrices of that size are equally possible. So in this case, it would be like a 3x3 correlation matrix for the intercept deviations, the deviations in the coefficient on age, and the deviations in the coefficient on gender. So your models could have been different, but they would probably have a lot of the same elements to that. And so, you know, this is kind of, you know, we've learned all kinds of things this semester, and we will continue to learn more things, and we're starting to learn Stan, but the Stan language isn't really all that hard to use. The difficult thing about doing a Bayesian applied analysis is really going to come down most of the time to thinking carefully through how to specify a model and to specify it completely rather than to just say, okay, you know, I'm going to specify like part of this. You really have to account for all of the unknowns and organize your belief about those unknowns, express it in terms of probability distribution. That is really the modeling aspect of this that is sort of really important for applied work, no matter what field you're doing in it. But it's not necessarily the sort of thing that we teach a whole lot in the QMSS. We sort of teach you, you know, how to work the computer for a lot of stuff, but how to specify a model is more of like a pencil and paper sort of thing. So, you know, in whatever field you go to, you're going to have more opportunities to practice that. But it is really, you know, Stan just facilitates statistical inference from a model. You still have to come up with that model. And it needs to be appropriate for the data you're trying to explain. So questions on the first one? Okay. So for question 2, when we start estimating, load up the data. This isn't so relevant for Stan Polar because it does this whole QR thing, but in general, it's good to scale your variables such that the coefficients that you kind of expect to get are neither too close to 0 nor huge values. And so if you sort of think about social processes are the sort of things that are asked about under the general social survey, you probably don't expect there to be a big difference between two otherwise identical people who are born 1 year apart in their views on social issues, even though, you know, age is probably the most important thing predicting your attitudes towards gay marriage during this time period. But if we divide age by 10, now we're saying like decades are our units. And it's more plausible that there would be, you know, a kind of not too close to 0 coefficient for two people who are otherwise identical but born 10 years apart on, you know, issues such as the sorts of things asked about on GSS. The outcome variable in VRMS needs to be an ordered factor, so I just made that ordered already, so unordered factor won't work. I just divided the data set up into something I called training and something I called testing. The training consists of all the years in which this question was asked, except the most recent one, which was 2014. I also made sure that the year variable was treated as a factor rather than some number that's like 2006, the integer. You would not expect there to be a lot of variation from year to year in the, you know, coefficient on a year variable if you treat the year as a number rather than as a category. So maybe with dummy variables. So then we load up our Stan arm. We can use the Stan underscore polar method equal logistic in order to use an ordered logit model rather than ordered probit, which we did before. Stan underscore polar, it's prior. Oh, Adam.
I'm curious about the treating the years factor thing. So, wouldn't there be some reason to think that the distance between the survey, say like in year 1988 2004, given that it's so much of a larger gap in between the next one, that distance is important, doesn't treat it as a factor, remove that?
So if in the first one, it said don't even put in year intercepts, but if year is a factor, then it's going to be put in as dummy variables for all of the subsequent years relative to 1988. So if there is a big gap, and there probably should be for this question, it'll be shown with like relatively large coefficients on those year dummy variables relative to the baseline year, which is 1988. Anyway, the first question somewhat artificially said, you know, do a fully pooled model that didn't have any heterogeneity across the years, so you could sort of see the differences in predictions that you got when you used, you know, more sophisticated things. But in something like this, you would definitely want to include heterogeneity over the years for this sort of relatively rapidly changing opinion on a social issue. So the Stan underscore polar requires you to express prior about the R squared in terms of the ability of this model to explain differences in utility for whatever the outcome is. Doing things with an ordered model, you should tend to use a lower number in general in the social sciences than for outcomes that are actually continuous. We just, as a social science, for most things, we don't really have great ability to explain why, you know, one person differs on a particular policy issue. We're pretty good at explaining like who's a Republican, who's a Democrat, things like that. But for the overall kind of bundle of policy issues, that is less noisy. But, you know, particularly if you study public opinion, you'll find that, you know, even people who have like, you know, conservative demographics will sometimes specify liberal opinions on a couple policies. So usually you're going to use a pretty low value for your R squared in something like this. I put in 0.3 as my prior mode. I specified 8 chains. By default, Stan does 4. That's often okay, but on the safe side, I usually do 8. I also specified the init underscore R argument so that the starting values would be constrained to the range -0.25 to 0.25. That gives more consistency in the amount of time it takes to do this. It doesn't have the property that number of you ran into where like 3 of your chains finish up pretty quickly and 1 gets stuck at the beginning and takes like a really long time to finish. If you squeeze down the starting values, then that is less likely to occur. Anyway, this model I think ran in like 3 or 4 minutes doing 8 chains for me. And then you can print out the results. These coefficients pertain to utility. So no surprise, people who are 10 years older have a pretty positive thing that puts you in more strong disagreement with the idea of gay marriage. Women, more supportive of gay marriage historically, etc. And you can see for the various religions, some being more open to gay marriage than others. You can see the estimates of the cut points. These are pretty spread out, which is a good thing. Like if you ask an ordinal Likert style answer and you get 2 cut points that are estimated to be really close together, it's basically saying, there's no one in the like little category here. So you might as well have used like fewer categories. But here they're pretty well spread out. And that's maybe not surprising because, there's certainly a full spectrum of, agreement and disagreement about gay marriage during the early 2000s, mostly. You get posterior predictive distribution for falling in each of these categories. So historically speaking, there was certainly a plurality of disagreement, but one of the things that, we saw, there was definitely a trend over this period. And eventually, nowadays the majority of people are okay with it. So questions about that first part. I also wanted to say that for some of these religions, the estimated standard deviation is a lot bigger than the others. And this is because in this data set, there was only one person who said like his or her religion was other Eastern, and like 2 people who said their religion was interfaith, non-denominational something, which is not even a real religion, etc. So a Native American, I think there was only 1 person, etc. So when you have these groups that they're just not that much data, it's going to be hard to estimate the coefficient on that precisely, but you sort of genuinely have a lot of uncertainty as to what, say Native American would think about gay marriage, because there's just not very many of them in the survey or any survey. So you have a lot of uncertainty, but that's uncertainty you should have. Yes.
So according to this, like if we take the age, we say 0.19 and the coefficient times x minus the cut point. Let's say the strongly gray cut point, which is like minus 1.31. And if we just do the logit inverse of that, and we plot that sort of becomes like 0.19x plus 0.131. That says like as you grow older, you read more.
You disagree more with the idea of gay marriage. So the way it's coded, the question is, homosexual couples should have the right to marry one or other. 1 is strongly agree, 2 is agree, and then 5 is strongly disagree. So what this is saying is for, otherwise identical people who are differ in age by 10 years, the utility for that changes by 0.19. And you can interpret this relative to the cut points. So it would basically, if you had someone who is like 20 and you multiply all this out, you got a linear predictor, and let's say you fell in like agree, but not strongly agree. So that would sort of put you in this area of the cut points. And then if you say, okay, if that person were 50 years older, we'd multiply this 0.19 by 5. That would shift the person over by about 1 unit. And so they started out at like maybe negative 0.1, and then you bumped it up by, what did I say, 50 years? You might expect a person like that to fall over the next cut point. And so these cut points sort of serve as like guideposts in this space of Y star for, how much you would need in order for you to expect a person to give a different sort of a response. Questions?
Standard deviation is pretty large. Some of these weapons.
About 0.14. So yeah, certainly that's bigger than the standard deviation on age. We're pretty sure about the relationship between age and attitude toward gay marriage. Less sure about where these cut points lie, but they're estimated a lot more precisely than some of the religion variables, even religion variables that are, reasonably common, like Jewish or something. Okay, so question 3. Do the model using BRM, which allows you to have LME4 style syntax. In this case, it just said, well, keep the coefficients constant over time, but allow the intercepts to deviate by year. So with that, you specify family equal cumulative. You can put priors on the common parameters in addition to the standard deviation in the intercepts from 1 year to the next. This one, if I left at the default value, had a little bit of problems with divergent transition, so I bumped that up to 0.9. Then it was okay. It gave me one warning message saying that there's some people who are NAs and they got dropped, but that's pretty standard for social science. So we can look at the results of this. What BRM calls intercepts are actually what Stan Pollard calls cut points. Cut points is a better way of thinking about these things. They're not really intercepts, in my opinion. So what you're really looking for here, the coefficient on age, the coefficient on female, the religions, etc. So these are all pretty similar to what we got before, even though we're now allowing the intercept to deviate from year to year. We're getting good R hats. We're getting good effective sample size. So, things look good there. And things look pretty similar to what we were estimating before. So we just line those two estimates of the common coefficients, or the coefficients which are assumed to be common, up next to each other. They're very similar. Yes?
So is that kind of, in terms of interpretation, kind of saying that younger people have always been more likely to support gay marriage, and that's been true?
Yeah, so I didn't look at the actual estimates of the Bs for the years, but presumably it was like a big positive number in 1988 at the baseline. And then, by 2002, in 2004, 2008, kind of everybody shifted rather than it being, particularly associated with the coefficient on age. So people get older, but the coefficient on age didn't seem to be that affected by this change in the model. But, we can go on to question 4 and allow not just the intercept, but also the coefficients to vary by year. This might, reflect some sort of, young people hang out more with young people, and like new ideas about social order and stuff spread more quickly among young people, something like that. Certainly plausible. Here I had even more difficulties with divergent transitions. So I had to bump adapt delta all the way up to 0.99 to avoid that. Yes?
About cumulative, cumulative. How different is it from categorical?
It's the same thing. So the default link function for the cumulative family is logit. So this is still an ordered logit model. And that, if you estimated an ordered probit model, then like these coefficients, they would be different, even though the predictions would be very similar. So yeah, both of these are estimating ordered logit models. The one in question 4 allowing the stuff to vary from 1 year to the next. This more or less corresponds to the priors that I wrote out in question 1 for my case. And you know, you can look at this. Certainly there's you know, bigger variation in the intercepts from year to year than there is on age or on gender. There's, you know, decent sized posterior correlation for the random intercept and the random deviation in the age variable, but overall this model is still going pretty well, and at least the common coefficients before you start deviating them by year still look pretty similar to what we were getting before. Effective sample in R hats are still good, so you can, oops, that should be post 4 right there. I'll fix that. So I compared 3 to itself, and they're identical. But they're not that different if I had done it correctly and compared 3 to 4. Question?
So how do you like draw the new, like, what are the nuanced questions that you would ask looking at the fact that these are sort of identical right now?
Yes. So, I mean, to get into the nuance, you would want to look at how these, you know, coefficients varied from year to year. And there wasn't much probably on age or on female, but definitely a pretty big amount of variation in the intercepts over time. And you should have seen that also in the previous question. Yeah. So it's basically saying that we just had a pretty dramatic societal shift on the question of gay marriage. And it was relatively rapid. Yeah.
I didn't see how to access the intercepts themselves. So, like, you're.
Yeah. So to get the posterior means of that, you can do RANF, or you can do as matrix, and you'll see all the things. Yeah. Nigel, you had a question?
Oh, yeah. So for BRMS, we call random extent as well to get the extent and the specific group level.
Yes. So RANF will give you the deviations, FixF will give you the common parameters, and CoF will give you the sum, which is the, you know, the coefficient in year T.
So how are this model will produce the intercepts for the, obviously for the years? It will also produce an additional intercept, the SD intercept, which is that SD intercept thing.
So yes, it allows the intercept to vary by year. It also allows the coefficient on age to vary by year. So there's only one set of intercepts. It's these year dummy variables. But also you have a year specific coefficient on age and on gender.
If you did 1 plus age plus sex in that at the end, then it would produce an additional intercept?
No, the intercept is implicit unless you take it out. So unless you do -1 plus age plus sex, then it's going to allow the intercept to vary from year to year. Usually we want to allow the intercepts to vary over time. It'd be weird not to. For Bayesian, frequentists do it all the time.
This will have a very
Yeah. Okay, so then you can go on to compare these using the Liu information criterion. And in my case, when I did it the first time, there was a warning saying some of the Pareto K estimates are a little bit too high. You can then plot that object with the label underscore points argument true, and it will show you the observation numbers for the ones that had high Pareto K estimates, which make the Liu IC converge to the true negative 1/2 of the ELPD at a slow rate. So even though you have kind of a lot of observations, if you have some observations that have high estimated Pareto parameters, then that is a sign that the assumptions underlying the Liu calculation, which are each observation has a negligible effect on the posterior distribution, are not being satisfied, which means you shouldn't be using the Liu to compare models, but also you might want to take a second look at those observations to see why the posterior distribution is so sensitive to them. And so in a manner of speaking, this Pareto K thing, it's kind of like a Bayesian version of Cook's distance that you may have learned about in regression models, but it works for all Bayesian models, not simply ordinary least squares. And so we have these 4 observations here. We might take a look at them. We can use the model frame to get back a data frame that was actually used. We want to look at those rows. And it turns out that these are the 2 people who said their religion was interfaith, non-denominational something, the 1 person whose religion was other Eastern, and the 1 person who was Native American. So this is saying the posterior distribution, at least some parts of it, are sensitive to these observations. Now, I think what it's really telling you is that not the whole posterior distribution is sensitive to those observations, but rather the estimate for the coefficient on Native American is sensitive to the 1 Native American who was included in the survey. And that makes sense. And so it's not really anything you need to worry too much about in terms of its coefficient, like affecting the coefficient on age. But in general, it might have been. So it's good to look at the observations that seem to be driving some parts of the posterior distribution. And in retrospect, it would make sense that if you only have like 1 person who claims their religion is other Eastern, the estimate of the intercept shift for other Eastern is going to be sensitive to that 1 person. But okay, so let's not worry about that too much. We got an estimate of that. I didn't actually print it out, but it was relatively high. We can calculate Liu for the models estimated by BRM, and we get lower numbers. So in this case, we get a slightly lower number for the model that allowed the intercepts to vary by year, but not the slopes of the coefficient on age and on gender. But the difference is really small. So basically it's saying both the model from question 3 and the model from question 4 are expected to predict future data from this data generating process about equally well. Now that already takes into account that model 4 is more complicated. So a lot of people like look at those and they say, okay, well, you know, maybe if the difference had been a little bit bigger, let's say this was like 6170 or something like that, and this is 6176, they're like, well, okay, model 3 is better, or you know, maybe the other way around, but it's more complicated, and they do sort of a manual adjustment in their head. It is already counted the complexity penalty when it's calculating Liu. And so here it's saying, well, yes, model 4 is more complicated, but given its complication, additional complication, it's not really expected to produce estimates that are or predictions that are that different from this other model. And in terms of explaining things, it's definitely good to go with the simpler model when they're about tied on the Liu information criterion. But that's more of a practical concession of explaining models. Then we can go on to predict what would happen in 2014 using the testing data, or a model frame derived from the testing data that throws away the missing observations. We can use posterior predict to get predictions for the held out data and calculate the number of times where the prediction was correct. That is about 22% for the first model, slightly higher, not that much, for the hierarchical models that I estimated with BRM. And as predicted, the one that varies only by intercept and the one that varies by intercept and slope are the same to 3 decimal points. So I wouldn't make too much of a big deal about the fact that the more complicated model predicts 5 out of 1,000 or something, or 10,000 more correctly. And it's also important to remember that this is sort of actual predictive performance for a particular data set. What the Liu information and the ELPD tell you is, okay, this is how we would expect a model it to perform, averaging over all possible future data sets. And so the Liu calculations, I think, are actually a better indication of what model has the expected benefits in terms of its prediction, but you got to watch out for the warning messages that it tells you when the assumptions of that estimator are not being satisfied. But there's way too much tendency to say, okay, this model predicted better in actual data, so I'm going to prefer it, without taking into account that the actual data set that you evaluated this on is just one possible data set. So I could have done another survey in 2014 of Americans and very easily found that Model 3 was slightly better. So you don't want to make too much out of one particular held out data set. It's much better to base your inferences on what model is expected to predict better for future data that come from the same data generating process. Question 6, we've now already alluded to. In something like a social issue or whatever, where opinion is changing over time, it would make sense to write down a model where there is some trend to the intercepts or maybe the coefficients over time, rather than saying like 2012 is a random draw from the distribution of years, when in the actual 2012 there was starting to be more and more court cases finding that the state bans on gay marriage were unconstitutional and stuff like that. So there's definitely a rapid trend in opinions over time. So it's not the case that the years are conditionally independent of each other. If I told you, what happened in 2008 with the year intercept, what happened in 2010, what happened in 2012, you or anybody else would be able to predict that soon there would be kind of a majority opinion in favor of gay marriage by like 2014, 2015. And in fact there was, although the whole thing, it was the US Supreme Court decision overturned those bans on gay marriage for the whole country. Questions about that? Yes.
Going back to question 5, so when you do the number, they say percentage of.
Yeah, so the posterior predictions were right for people in 2014, 22.3% of the time. So considering there was only 5 categories, that's not overly impressive. Like you could have guessed equal probability in each category and you would have come up with something pretty close to that. So our model only gives us a little bit of additional explanatory power. Even though this is probably one of the social political issues that's thought to be best predictable compared to some other stuff like death penalty or whatever.
Like you see this trend in the data also, right? Like you, in question 6, what you said was like, there's some anecdotal evidence.
Yeah, other surveys and whatnot.
Yeah, but
I mean, it was a pretty clear
in the
trend.
data, you see like a systematic trend somehow that suggests auto correlation.
I didn't look. It was evident in the model. And I prefer to make the inferences off the model than off the data. But I think if you looked, yeah, you'd find that. Yes.
So in model series when you respond to model, is it useful to also see how your predictions, if they are wrong, they are not as wrong?
Right. So there's, if you predict 5 and the person was actually 1, that's, worse than predicting 2 and the person was actually 1. So you could dig, more detail into that. And my guess is you'd find your model is giving you, a little bit more precision than if you just, averaged over the whole data. But yeah, that is a worthwhile thing to look at. Other questions?
This is a lambda function that says E2 compare E2.
Yeah, E2 is the right-hand side of the equal function. So yeah, take each one of these, go row-wise, compare it to the actual data, and see if they're the same.
So in this case, would you recommend using as integer or just like the first?
Oh, unfortunately, in my opinion, the RMS, it does posterior predictions of ordinal. It outputs integers as opposed to factors or characters. So I had to coerce my thing, which was a factor, which is correct, in order to compare those with the equality operator. Yes.
So in that function, are you finding a match for each draw and then averaging it out for each observation?
Yeah, so posterior iteration 1, I get predictions for all 400 or whatever people there were in 2014. C of those, iteration 2, iteration through 8,000, and then take the proportion of correct over all that. All right. So hopefully we learned a good bit from that. Want to go on and continue talking about writing and executing models in the STAN language. I do not want to talk about the fact that I'm an employee of Columbia and a co-founder of STAN Group, but I have to. Okay, so let's think back to, I'm actually going to switch over to our studio for this. The simple model we did way back at the beginning of the semester for will U.S. doctors who contracted Ebola during 2013 survive if they take this experimental drug that was made by MAP Biopharmaceutical. So we did that analytically at the time using the fact that the beta prior is conjugate with the binomial likelihood. But how would we do something like that if we were writing in the STAN language, which is what we're doing these days? So if you want to create a STAN file, you can just create a text file in RStudio and then save it with a .stan extension. So if I do like whatever, Tim. .stan. Then RStudio will recognize this as a STAN file and do like syntax highlighting and other things to make it easier. It also has the STAN or a STAN icon to indicate this is a STAN file. So if we wanted to write a STAN program in the STAN language for analyzing the Ebola data, how would we go about doing that? Yeah. Okay. In this case, I don't think we're going to need any functions. this is a sufficiently simple thing that I think we can just use the functions that are already built into Stan. But we could start with a functions block if we wanted to. A lot of people find it easiest to actually start at the end, or, toward the end, with the model block, and then figure out what pieces they need in order to get to that. So in the case of the Ebola thing, you can't see them. Does that help? No. Can I shift the whole thing over? Now you can see. Okay. Okay, so in the case of the Ebola data, what would we want to do in the model block for our likelihood?
What's the task here?
We want to estimate the probability the drug is effective.
Right, the likelihood function.
What is the likelihood function we need to use here?
It'll be like
Binomial. So target plus equal. Binomial, except everything is in log. So the function we need to use is binomial underscore LPMF, log PMF for the binomial. And then what are the inputs to this built-in Stan function? Or we haven't used this yet, but for any binomial, what would be the inputs? Right, so there's three things we need to account for here. Probability of success, the number of successes, and the number of trials. So this would be something like, lived, conditional on infected, and P, for let's say the probability. Now you do need to look up the arguments to know what order to specify them. I'm pretty sure it's the case that the number of trials comes before the probability, but in Stan, everything has to be specified by position. Okay, so the number of people who lived and the number of people who infected, those will be data. So that's going to come in the data block. How would we specify those? Maybe it'll help if I make it bigger.
like trials. So,
yeah, so that would maybe work for a Bernoulli model, and a Bernoulli or binomial is the sum of independent Bernoullis. So in this case, if we assume the people are independent, we don't actually have to put in multiple numbers. We can just give the total number of lived and the total number of infected. But what data structures would we want to use for those two things? Integers, good. And these, of course, have a lower bound. So we can do infected. We can even do something like this. Right? Because the number of people who survived Ebola can't be greater than the number of people who contracted it.
when you say infected, that's who got infected with the virus and became sick.
Yes, or U.S. doctors. there were thousands of people in Africa who were infected, but the only people who had access to the experimental drug were doctors and nurses and stuff from Western countries. At the time, they only had like 7 doses. So they prioritized giving it to people who are medical professionals. Yes? Which line, this one? Yeah, so infected is going to be an integer, and it's going to be non-negative. In fact, it was 7. So we're going to pass the 7 from R to Stan. And we're going to give it the symbol name infected. And the number of those 7 people who lived, that was 5. So also an integer between 0 and 7. Right. It could be 0. It's interpreting inclusively. But it can't be like -1 people infected with Ebola. Doesn't happen. All right. So what more do we need here to do a posterior distribution, or to specify a posterior kernel in log units? Okay. Prior on the probability of cure, right? So before we even do that, we're going to need to declare in the parameters block what this P is. So what would we declare for P? Real number. Okay, that's appropriate for a probability. We could even give ourselves a comment. Okay, so we've declared the parameter. And then what was the prior distribution that we want to use for this probability? Beta. All right. And since beta is continuous, it's LPDF. All right. And what are the hyperparameters to the beta distribution? Yes. So these are going to be things you specify. It's 2 shape parameters, no rate. Rate is for gamma. So we can call these alpha and beta. All right. And then where do alpha and beta get declared? Could. What we did in like week 2 was to specify them as data or knowns because we had trials on monkeys. All right, so like 14 out of 21 monkeys survived if they got the cure 3 days after they got the disease. Something like that. And so we used those to form, you know, when we had the clicky thing and we made distributions and we moved it left, moved it right, you said where to stop. So we sort of formed implicitly our beliefs or specified alpha and beta that way. Here, we're going to have to do it as numbers and numbers to be passed from R to Stan in the data block. So what sort of a declaration do we need for these alpha and beta? Real? what amendment do we need to real? For the case of a shape parameter of a beta distribution? Okay. What about 0? Lower equals 0. Yes. Shape parameters to a beta distribution cannot be negative. All right. So that right there is sufficient. If you click on the check thing in RStudio, it will tell you that this is a valid stand program in terms of syntax. It can always be substantively terrible, but it's valid syntax. You don't have any undefined variables or anything like that.
When you call this file or the model, do you, if you want to pass draws, like number of trials, like coding example, for example, have number of trials, that kind of thing. So do we give like, do we specify that we change the data to have like vectors, or do we like do it outside, vectorize the functions on that?
No, so once it goes to Stan, R, it can't talk to Stan, can't talk to R until it's done. So it's not like you can define R functions or anything like that. What we did last time with the bowling, we had to pass in integer arrays, not vectors, because vectors are real numbers.
Just trying to think what the correct programming thing is. Do we make an array outside? Do we declare it there and pass it?
And pass it in, yeah. So just to show you how you would estimate something like this, using RStan, you can copy a line like this. So library RStan, options, MC cores. Another thing that RStan will suggest to you is auto write equal true. This will save your compiled models in the same directory as the .stan files. That'll cut down on time wasted compiling the same model over and over again. So if I want to, oops. When you do this, you need to specify a full path to the Stan file if it's not already in the working directory. So I could, mine are in temp, or what I could do is instead set the working directory to temp. And then this will work. And the way you do this when you're calling the Stan function from RStan is to pass a named list of data whose names are the same as in the data block of your Stan program. So if I just do this, I'm going to get an error message after it compiles. This is a little bit annoying. It's going to compile before it gives me the error message, because here I said y equals 5, n equals 7, rather than live equal 5, infected equals 7. So you have to use the same names. It's going to take a little while to compile the C++ version of that. And I get this error message. So if I do infected 7, lived equal 5, then it doesn't have to recompile it. It can just run. Okay, so that takes almost no time. Then you can look at the results. This is a little big. There we go. So it estimated P to have a posterior mean of 0.69. You know, you can look at the median, you can look at the quantiles, had a good R hat, good effective sample size, etc. A lot of the things that you can do with one of these that comes out of Stan. So that's a real annoying feature of our studio. You could look at a pairs plot. In this case, there's only one parameter, so it's not all that interesting. You can pass this thing to Shiny Stand with the launch Shiny Stand. I'm not going to do that right now, but it also works with these objects that are produced by Span. You can convert the thing to a matrix. In this case, it'll be 4,000 by 2. And the columns of that, the first one is P, and the second one is the log kernel value of it. So you can do as matrix, as data frame, etc. There's also a function, unfortunately, named extract, where you can extract particular dimensions of a posterior distribution, etc. So yeah, the thing with our main thing, you need to pass the data as a named list that matches up with the declarations you gave to those things in the data block of your Stan program. Questions?
And gets stuck. Like the launch and stand launch gets stuck.
That when it has really large objects, yes.
Yeah. So like when we get to like say more of why it's getting stuck or something.
It's not getting stuck. It just takes a long time. It's doing a lot of stuff. So that's talked about in the documentation. You can actually cut down on the time if you know, like, I don't want to see certain plots, then it doesn't have to make those. It's talked about in the Shiny Stand documentation. Other questions? Okay. So let's say we wanted to do a slightly different model. Where the probability of survival depended on how long it was until between the time you contracted the disease and you first got the cure drug. So if we want to make your survival probability a function of that time gap, how would we write a model like that? How would we change the model that we have now? So let's say different people had different amounts of intervening time between when they got Ebola and when they got the Ebola drug. So time elapsed is like a covariate. So you think you have a higher probability of surviving if it's like a week between when you get Ebola and when you get the Ebola drug, or if it's like a day? Right, you have a higher probability. So we have a reasonably strong prior belief about the direction of the effective time. Maybe something like that. But let's think about, okay, what would we need to do different to incorporate time into a model like this? Yes.
Put a parameter and you just scale based on that.
Okay. So we could have yeah, something like this where we could have like p times time, something like that. We can incorporate that. So it's more, now it's like the coefficient on time. So maybe I better call this beta rather than p. Okay. what do I need to do with the data block? True. And now if, different people have different amount of time between when they were exposed to the disease and when they got the cure, now we no longer can use binomial because we're not summing independently and identically distributed Bernoullis anymore. Our Bernoullis are associated with people who got the disease and got the cure at different amounts of time in between. So how would we need to specify the data pieces in a situation like that? So we have 2 pieces of information on each person, each of 7 people.
And they were inoculated.
Right. So we know if they survived, and we know how long it was that they were untreated. Yeah, of the time, right. Okay, so how would we specify 2 data structures like that? It has an integer type. Or weeks, whatever. I think it was days, historically. Now, if we have 7 people, what are we going to need to do different? What? Treated or not? Well, they all got the drug. And
So if there are 7 different people, we have 7 different times.
uh-huh.
So in the space,
So in here, you got something like integer arrays. And so now if we are thinking about the data on the individual level, whether you lived is just 1 0 variable. All right. Now, before we can declare integer arrays of length n, what is it we need to do? Specify what n is. All this comes from the outside. But the nature of n is such that it is an integer, has a lower bound of 0, and it is named n. So yeah, we're going to pass all 3 of those from the outside. Okay, back to the model block. So we were going to specify a likelihood for something like this. So this I've called days rather than time. Okay, so that's part of it. What's the actual likelihood we need to be using here?
Maybe the exponential negative
Logit. So how would we specify a logit model in Stan? Yes, so you can do something like this using the inverse logit link function. Actually, it turns out it's better to use the Bernoulli logit function, Bernoulli logit underscore LPMF, which combines together the logistic inverse link function with a Bernoulli likelihood, and it inputs eta, which is eta times the number of days. So what else would you assume the Bernoulli likelihood inputs? Bernoulli likelihood of yes. The probability a person lives conditional on the cure coefficient multiplied by the number of days in between the time they were infected and they got the drug. Okay, that's the likelihood for a logit model. What do we need for the posterior kernel? Prior. What sort of a prior might we want to put on our parameter here?
Data has to have prior on it.
Yes, it does. What prior would you like?
It will be like rapidly increasing so that the probability increases.
So you're saying you think it's negative?
Goes really fast downwards.
Toward negative infinity. Plausible? Okay, so, you know, that's more specifying a function. So here we're saying it's a linear function in time. That may not be right. But if you were going to specify a linear function in time, what are your beliefs about that coefficient? Should be what? T? Okay, I heard uniform. But uniform between what two numbers? Well, Y-ball, no. I mean, that is a probability distribution. That is a probability distribution for non-negative quantities. So if we were to put a Y-ball prior, you would be saying it's guaranteed this coefficient beta is positive, which is to say, as more and more days go by, when you're untreated for Ebola, you have a higher and higher probability of survival. That is a biologically dubious theory, according to all the people who died of Ebola after like 10 days.
Can it be uniform between 0 and -0.1?
Could be. If it were, then we would want to specify a lower bound. Would you say negative 0.1? All right. That is valid stand syntax. However, not really advisable because if the if the actual coefficient is outside that interval, you will never learn it. So you're saying there's 100% chance it's between -1 and 0. So I'm with you on the upper bound, but I don't know that I would necessarily put in a hard lower bound. It's a little hard to think in terms of log odds, like what the right number for that could be. Upper bound is 0. Now you're only making the assumption that the drug doesn't make you worse off. Still, for an experimental drug, I don't know if I'd go that far. You could, your beliefs. But, you know, drugs have been known to kill people too. Not as fast as Ebola, but it's been known to happen. Nigel?
The normal distribution.
Normal. Hard to go wrong with the normal. Okay, what has the normal distribution? Yes, there's going to be a mean and a standard deviation, but we're putting this on beta. Okay. So what would you want to put for the mean and the standard deviation of this normal prior? -1. That was a mean rather than a standard deviation. Good. Higher standard deviation. .5. That's good. So you're saying there's a very small chance that it's greater than 0? So 95% of a normal distribution is within 2 standard deviations of the mean. Very small chance it's less than -2. So this probably wouldn't be too bad. It would be better if we declared those as data. So we could pass them in from R rather than hard coding them in a Stan program, so that we would have to change those every time we changed. Different people might have different beliefs about that, but here we have a syntactically correct Stan program, although there's some warning messages previously. Oh, this is actually not syntactically correct. Yeah. So the multiplication operator, that's actually only defined for vectors and scalars. So I am going to change this to a vector, which is, you know, usually no big deal for a predictor, whether you call it an integer or a real number. In this case, it's a real number, but there are no decimal points. So this is going to be okay now. Come on. I put the N on the wrong side.
The placement of the N is kind of confusing.
Yeah, you do it differently for real versus. Now what's my problem? Oh, I put that in the wrong place. I meant to change Bayes to a vector. Okay. So all that is a logit model with one predictor, no intercept, and a normal prior. Could have done that with our Stan arm, but you can write it yourself in the Stan language. You really need to practice the process of specifying these models. What's the nature of the data? What declarations do I need to do to it? You know, what's the likelihood function? What are the predictors? How are the predictors related to the linear predictor? What's the link function? Then, you know, when you got all that, okay, what are my prior beliefs about all the unknowns that I've declared in the parameters block? Here we didn't use transform parameters or generated quantities, but you may want to utilize those as well when you're specifying models like this. Okay, so pick it up on Tuesday. We're gonna have to rearrange the schedule a little bit, so I'll post a new syllabus that has different readings than the ones I originally planned for Tuesday. But Tuesday we're gonna have more practice like this, specifying models in the STAN language. Okay, see you then.